about these. I gave you a way of processing the lab and then talked to you a little bit about the idea of the angle and may have, confused the issue a little bit yesterday. You have to approach this problem from the standpoint of all of these force problems. So if you're not doing that, I'm not sure what you're trying to do. When I was going over this last night with a certain somebody who shall not be named, who came back even today to ask more questions, the number one problem that he had is he kept wanting to jump at an answer, like apply some formula he solved somewhere else to the problem at hand. That's not going to work. And as you've come to find out, this isn't a plug it into the equation and kind of let it go kind of situation, is it? That time was earlier this year when I said things were easy and you could use the motion equations. That was the only time in the year where you could just plug stuff into a formula and get an answer. Every other time this year, you need a procedure. Look, you have an equation sheet with like 50 odd equations on it. Is that helping? Having equations isn't it. And it never has been. So start at the same place I tell you all of you to start. Draw yourself a picture and ask yourself what's happening. Is it a first law problem or a second law problem? My understanding is that the object is being spun on a string. So I start with quick picture. Spun on a string. This is a sideways look, and it's going around, like that. I don't know how to draw this because it's kind of three-dimensional, right? So I'm not sure. So maybe that, this to me looks like, and it's kind of making a circle like that, like a tether ball. Does that help? I'm trying to find things in your life or like the lab I put in your hands. And this is 15 degrees. And we're told that the string is 1.2 meters. Well, from a top-down perspective, that's what it looks like for the ball, right? Top-down perspective. And this is the string, but this isn't the length of the string. This is the radius, right? That would be more like this line. If we're looking at it from the sideways vantage point, that would be the radius. We know the object's traveling in a circle. So now that we've kind of got that all hashed out, let's consider how we would solve this. And I think Newton's laws is the only way. And the reason I believe Newton's laws is the only way to solve this, there's a couple of giveaways. And look, right now you're on a Newton's law chapter, so choosing Newton's laws to solve these makes perfect sense. In April, when we're no longer on any chapter, and I just throw a problem in front of you, what are some telltale signs that it's a Newton's law problem? Centripetal motion, telltale sign. It's a Newton's law problem. Okay, if you know the object's traveling in a circle, you're likely going to use Newton's laws. There's no other replacement for problems that have an object traveling in a circle. So start to come to grips with that, because the next unit is to try and find a way around using Newton's laws. And so we'll find ways around it. But in this problem, you have only Newton's laws at your disposal. So start with the free body diagram, of which I think there's only two forces. Those are my two forces acting on the object. And I expect the object to be experiencing unbalanced forces. It's traveling in a circle. It has to be unbalanced. Therefore, net force in the x direction, I'm going to make MAC, and net force in the y direction, I'll make 0. And I'm going to choose purposefully to have, the x direction be this way. I'm could have positive x and positive y. So I'm going to break the tension up. It's an off-axis component. If you don't know why I made this direction the positive x direction, is that's the direction of the centripetal acceleration. It's the one that points from the object towards the center of curvature. I can't make this the positive x direction. That's not the direction of the acceleration. The acceleration is towards the center of curvature. I've said that in class before. I just want to make sure you are getting that. So, continuing on, I will have a tension in the x direction, which is going to be t cosine 15. And I'm going to have a tension in the y direction, t sine 15. I hope you notice that all I'm doing is the exact same procedure I've been doing since we started forces. Have I veered from it in any way? Okay. I'm going to continue. Now, you might think there's other forces, but there's not. The thing is not in contact with any other surface, so no normal force. Unless we are bringing up drag, there's no air resistance. So now I'll say net force in the x direction equals mv squared over r. I'm choosing this because it asked for the linear velocity. Now, if it also asks for the angular velocity, but I'm doing the problems in order. If you want to do angular velocity first, then use omega squared r. I don't care. Pick one. Do you care which one I choose to do? Because you have to find both anyways. So I'm going to start here. There's only one force in the x direction. T cosine 15 equals m v squared over r. All right, that doesn't get me very far, but I do know one more thing, and this blew somebody's mind yesterday because they kept not understanding it. But r has to be L cosine 15 as well. You guys see why that has to be true? If not, I can explain it better, but it's just a triangle. Okay, so we'll use that in a minute. Let's keep going. Because, to be honest with you, I don't know what t is. So it's not like I can solve this for the velocity. I don't have the mass either, I don't think. So although I have the length of the string and I have the angle, I can't solve this, not in this way. So I'm going to keep going. What is it, Christopher?
What does the L stand for?
Length. They gave me the length of the string. It's a length, it's in meters. L seemed appropriate. Would you like a different letter? Excellent. So, I'm thinking look at the y direction. Right? I haven't finished the problem yet. Maybe there's something I can get from the y direction. Because this is not enough this thing right here is not enough to solve the problem. So in the y direction, I'll have t sine 15 equals mg. Any question about that? Now, I've said this in here before, but maybe you don't remember. If you get something that has a t sine 15 and a t cosine 15, you have sine and cosine in the same problem, join those together because you know that makes tangent. So I'm thinking maybe set these up so that you can do a division problem. Right, this is not the first time we've done this. It's a math thing. You have to eliminate t and try and eliminate m. This will do both at the same time. So t sine 15 divided by t cosine 15 is tangent 15. And mg divided by mv squared over r. Well, I'm going to write that out because I know some people will flip out if I start canceling stuff out. So I'll just do all of that, but that's not the best way to go because I can cancel the m's and I can multiply top and bottom by r. So that gives me tan 15 equals rg over v squared. That's it. That's pretty straightforward, isn't it? Not done yet because I can't have r in my answer. But I have expression for r, It's in terms of something I am given. So v squared equals L cosine 15 times g over tan 15. L is 1.2, G is 10. There's your answer. That's how fast it's going. We couldn't do this in the lab because we couldn't measure the angle. And that's what I said in class. We can't measure the angle. If we could, we would do this in the lab. Certainly easier than what we had to do, right? But it wouldn't give us what we wanted, which is a relationship between the tension in the string and the speed of the velocity. So maybe not. Do I have to do any more for this problem, or is that pretty good? See, silence. So I must assume pretty good. Could you do this on a test tomorrow? We'll find out. Maybe today, in just a few minutes. I love that. A sigh. It's a sigh of relief because now you understand what to do. Right, that's the other answer. But that'll be in radians per second. You'll have to convert it to RPMs. Move on. Bug on a record player. Problems. If you want these problems in some way to provide you some kind of benefit, one of the things you should be doing is working the problems out without using any of the numbers, instead of always plugging the numbers in first case. That's going to serve you in the future in a way that I can't fully emphasize. If you work the problems out symbolically, what you are going to get is a reusable solution that often applies to other parts of the problem. You make more work for yourself putting the numbers in right away. Because when you put the numbers in right away, you often have to redo everything should a parameter change. However, some of you take that to the extreme. Last night, several people that came to tutoring talked to me about things they saw in their homework and were trying to plug stuff into things they had solved for or things that I had solved for in the homework, without understanding that they were not relevant to the problem they were working on at the time. On this bug problem, you're going to notice that regardless of the situation, I approach every problem with a procedure. Your apt refusal to use my procedure is why you fail. And I target everybody who came to tutoring last night. That's why you fail. You don't want to follow the procedure, or you don't understand the procedure. But I have never started a problem without having a plan on how to solve it. And I've given you that plan. Look, you have an equation sheet with like 60 odd equations on it. Have you ever been able to plug something into an equation and just get an answer? The answer is yes, once. Kinematics. And we saw how well that test went for some of you. It will never happen again the rest of this year. The equations are not the answer. You will create something new in the course of doing the problem. You must understand the procedure. So the bug is traveling on a record and the record is spinning. The only way the bug can stay on the record is if there's an unbalanced force directed towards the center. Now, for every person who's hearing that and didn't know that, just write it down. Because that's the important part, that this is a Newton's second law problem and must be solved using Newton's laws. You see, you're worried about the next test. I'm worried about the test in April, when we've done all the content and we're practicing, and I hand you a problem, and it could be anything in our curriculum. How are you going to know whether to use forces or conservation of energy or the work energy theorem or something about momentum or something about simple harmonic motion? How are you going to know? You need clues. I'm giving you those clues. And this is why your notes fail you, because you're busy looking at me. I know that the only way the bug stays on the record is if an unbalanced force is towards the center. Otherwise, they will travel in their last straight line path. So for the bug to stay on the record, there must be a unbalanced force this way. And that force has to cause a centripetal acceleration. So now I'm going to attempt to analyze the forces on the bug, because this has become a force problem. I will start with a free body diagram, and I will draw the forces in as I believe they must exist based on the preset notion of how forces act. I don't make anything new up. I'm following a procedure. Weight downwards. It's in contact with the record. Normal force upwards. What is the only other force that could possibly be acting to hold the bug in place on the record? Friction. Why? Because friction keeps an object from sliding past its surface. Now, I'm saying all of these, but I'm remembering the questions I get last night. And every question I had last night, I had already answered in class once or twice or sometimes 3 times. Is there anything new here? Any surprises? Remember, you asked me about this question. So yeah, I get a little salty when, when I stay up for 2 hours tutoring. So next, to apply the rules, I'm supposed to choose a coordinate system that will assist me in organizing the forces in the x direction and the y direction. I don't think there's a whole lot to do in this problem because they all appear to be lined up. But again, it's a procedure. I'm supposed to choose the positive x direction to be the direction of my acceleration. Again, that's something I am adding to this set that I think makes the problem easier. You don't have to do it this way. There are alternatives. If you want to use an alternative, though, be careful about what alternatives you choose to do. But I am going to follow this procedure and make that the positive x direction and that the positive y direction. I'm noting that there seems to be a balance in the y direction, but not a balance in the x direction. So I will say net force in the x direction equals MAC, and net force in the y direction equals 0. There is one force in the x direction. And based on the information that has been provided to me, it makes the most sense to go ahead and use an expression for the centripetal acceleration with the parameters I've been given. An angular velocity and a radius. At the same time, I have an expression for the normal force. Any questions about these choices yet? All right, that's it. That's the end of what Newton's laws can do. Hold on just a minute. So, this can't solve the problem. So there must be something more about the problem that we need to do. Well, the problem wasn't just about this. The problem was about finding the coefficient of static friction. It seems likely that we might need to use an expression that at least has the coefficient of static friction in it. So let's consider that there is an expression that has the coefficient of static friction in it. A relationship that tells me how the normal force is related to the frictional force. And that's what this is. So if I want to solve this problem, I'm probably going to need this. This is where the coefficient of static friction lives. But I've also suggested to you guys that, it's nice to be able to preserve the inequality. Now look, we've reached the point in the problem where we're done with what the procedure can give you. This is where you have to stand up and do the problem yourself. Be aware and cognizant. What are you allowed to have in your answer? What are you not? With numbers, that's pretty easy. You know you were given an angular speed and you're given a radius. You weren't given the mass of the bug, but you're asked to find mu. Well, you could just start putting numbers in places and doing cancellation. That's not how I taught you to do it, though. I suggested perhaps you try doing substitution in this form to remove things that can't be in the answer. Normal force can't be in the answer. Remove it. You can do some substitution, right, like that. The actual size of the friction force can't be in the answer. Remove it. Do a substitution that contains objects that can be in the answer. Stop worrying about the fact that you weren't given the mass. That's the first thing you guys tend to say at the beginning of the problem. They didn't give me the mass of the bug. So, Worry about that at the end if you can't find a way to somehow get around it. Stop worrying about it at the beginning. That's nothing will infuriate me more. So I now have m omega squared r is less than equal to mu s mg. We were asked to find the coefficient of static friction. Well, that exists here. And I'm noticing that the inertia of the bug and the weight of the bug cancel out. Right? We have the gravitational mass here and the inertial mass here. I'm only speaking to the people who are with me right now because there's some people who don't understand that and they're busy trying to figure out why the m is there in the first place. I'm not talking to them. I'm talking to you guys who want to understand more deeply what's happening. Inertial mass is this m. It's what's resisting changes in motion. It's why the spider wants to fly off the record, not because of gravity, but because it has inertia. It wants to travel in a straight line. It requires a force to change its direction. This m is gravitational mass. They come from different places. And it's just fortunate that they cancel out. There will be a time in your future where the thing that causes the force isn't the weight. Right now, the weight is pretty pinnacle, isn't it? Without weight, there'd be no normal force, there'd be no frictional force. It's all hinged on that. But there will be a time where other things cause a force, and the mass won't cancel out any longer. The mass is canceling out because gravitational mass and inertial mass are the same. It's convenience that led to there being motion equations. The fact that we could do all that work without knowing what the mass was, which is why they kept throwing the mass in there to distract you. You may not remember that, but a month ago they did. They'd give you the mass and the problem and you would never use it. You're supposed to have an understanding as to why now. All right, that's enough of that, really. Once I cancel this out, you have a way of writing the coefficient of static friction in terms of the other variables in the problem. And if you've done this correctly, you should understand why it's greater than. It's telling you that the coefficient of static friction must be greater than whatever is on the right. So you want to find the minimum? The minimum one is the one where they're equal. It can be bigger than that number. It cannot be less than that number. That's how a greater than symbol works. I am not convinced you know that. I'm certainly not convinced by the ways people were talking about it in the last couple days. But there, that's it. That's the answer. And you can use it for the next part of the problem. Right? When you start changing parameters of the problem, how far can the bug walk if the coefficient is this much? You've got it right there. I didn't put any numbers in, so I can mess with the parameters now. Right? I can solve this for R. Redo the problem. Maybe they want to speed the record up. Okay, great. Solve it for whatever. See, but you've created something new that now can be used to figure other things out. That's why I would do it this way. I don't care what the answer is. If we look top down on the object, if it's spinning like that, the radius is going to be this straight line as the object spins around the circle. So to me, that's got to be this line. That's got to be the radius. Everybody good so far? Understand why I have to say that? That's the distance from the center of curvature. So I'm going to make that the radius, which L cosine theta. Assuming this is theta, that makes this theta. So it's L cosine theta. It is a length. Okay? Now, the only way this ball travels in a circular path is if the net force is unbalanced. This is a Newton's law problem. I'm going to start with Newton's laws, which means I'm going to start with a free body diagram. You understand, I'm about to do the exact same speech I just had a minute ago, right? All the same things, all the same stuff. I am not going to change my procedure at all. So if you jumped in and looked at all your lab stuff, the lab stuff was a different derivation than this. Everything about the lab stuff was different. We had a weight that were hanging down the center. We were trying to make that an equal value to the tension that was acting on the stopper. We did a whole bunch of things different. So you can't really apply the result that you determine in the lab to this directly. It's a different set of parameters. You must start fresh with this problem. I see a force in this direction, I will call tension, and a force in this direction, I will call weight. Any question about those? I need to create a coordinate system that is lined up with the direction of the acceleration. Well, that's got to be an x direction that's this way. I'm going to make that the positive x. That has to be the direction of the acceleration because that is towards the center. It lies along r. That has to be the direction of my acceleration. I think in the y direction, it's going to be balanced. Right? The stopper doesn't fall to the ground nor accelerate upwards. So I will now draw the two components. This one, t cosine theta, where theta is here, and this one, t sine theta. Questions? I'm going to continue my procedure. And my procedure tells me to take Newton's law and break it up into the x direction and the y direction. Net force in the x direction equals MAC, and net force in the y direction equals 0. In the x direction, I see only one force, t cosine theta, which is going to equal, in this case, mv squared over r. I'm deciding to use this expression because they want the velocity. They say it in clear terms. What is the velocity of the stopper? They also want omega, so you could do omega squared r too. I'm just answering question A. Now I also know that t sine theta has to equal mg. That's the net force in the y direction, and it must be balanced. Right? Now, that's it. We get nothing else from this. Anything else we do, we have to kind of work out on our own. So you need to figure out what you have to do here. Now, I've kind of said to you guys, if I see a sine theta and cosine theta, that screams tangent. And I've talked about that in here. But look, what can you use and what can you get rid of? We can't have tension in our answer. It wasn't given to us. We can have G in our answer, sure. We can plug in 10 for G. But they never told us the mass of the ball, so we have to get rid of that too. But we do have the angle. Now, you have to find a way to eliminate the things that are not supposed to be in your answer. And again, this is a point where I can't help you. You have to do this. This is why you passed Algebra 2. But I have given you some tools. And one tool that I would use here is to consider that you could stack these things. Right? You could take all the stuff that's here and use it in a different way. And I like doing it this way because it solves lots of problems at once. When I see something that's t sine theta and t cosine theta, and that's happened a bunch of times in here now, then I see a way to get rid of the t's right off. And that's to divide one side of the equation by the other. So I'm going to divide the left side by cosine theta and the right side by mv squared over r. We've done this before where I've stacked the equations and I've divided to get tangent on one side. If you don't want to do it this way, then don't. Solve for t in one and plug it into the other. You have methods here. And my expectation is you use your methods, whatever you feel comfortable doing. But this is what I feel comfortable doing. The m's cancel out. How convenient. Now, this isn't expressed great. That's better. Now, you can solve this for v squared if you want, but we have another problem. R can't really be in our answer, can it? But we have a way to get R, but because, I like substituting and getting one expression, I'm just going to substitute. So, seems to me that we could write this as v squared equals GL cosine theta divided by tan theta. There you go. That's how you get v. I mean, all of this is just algebra. None of that is particularly interesting. The hard stuff, getting to this point. That's the physics of the problem. I'm expecting you guys to come to the class with the algebra. But I'll help you. Once you get V, you can get omega. Right? Once you have this, you can just convert. You're going to have something that's some, meters per second, but you can get, omega from that because we know that V equals omega times R. So omega's got to be V divided by L cosine theta. I'll write that there because if I don't, somebody's going to do it wrong and I'm going to be frustrated. There. This comes out to radians per second though. If you do all your units correctly, you're going to have something for V that's going to be in meters per second. And you'll be dividing by meters. That leaves you with nothings per second, which is radians per second. You'll have to convert that to RPMs like the problem asks. I assume you guys can do that. An assumption I made in sixth period that I was wrong about. Well, that was fun. But I'm going to say it again, and this is not just for any one. What I'm really doing in this step is dividing both sides of the equation by the same thing. So if you want like an intermediate step to make you feel better about it, I'm really dividing both sides of the equation by t cosine theta. That's what I'm really doing. But I also know from a prior portion of the problem that t cosine theta equals mv squared over r. So before I actually do the division, I'm slipping in here and replacing it with something that I know equals it.
And that helps you because you have.
Well, yeah, it helps for a lot of reasons,
I mean, you wouldn't do it in a problem when you don't have.
I might, and I have. Is that the one we're talking about now? I don't know why that one's so hard. Bug on a record player. I don't even know what the problem is. I'm just going to talk about the problem. But you guys, you could interrupt me and tell me what the problem is. But is it a bug is somewhere?
It's 12 centimeters from the center,
12 centimeters from the center.
and it's spinning at 33.3 RPM.
33 and a third RPM.
And then it says, what is the minimum coefficient of static friction that must exist between the bug and the record? And then it gives the actual one. And asks how much further could the bug walk away from the center?
All right.
If the record maintains 70 meters.
I think this is a problem that we can solve symbolically. And if we solve it symbolically, it'll answer all of those questions. I know you guys love putting the numbers in. Do you notice I never put the numbers in? There's a reason for that. I like to reuse what we get here. If you put the numbers in early, you never get to reuse anything. But if you wait to put the numbers into the end, it serves two different purposes. Purposes? But it's porpoises or porpi. Octopuses is octopi. Purposes, is that really a word? It's not purpi. Are you sure? Okay. It serves two different purposes. One, I think it allows you to see how the variables are related for questions like this. Right? You're going to be asked, where does the bug get to walk until it flies off? Well, if you know how they're related, you might know whether it should be walking towards or away from, how it's going to affect the answer, all that. Second, most of the problems on the exam are symbolic. If you want your homework to help you, do the problem symbolically first. Plug in the numbers later. If you're given a problem on the exam that has numbers, it's a bonus. Right? That way you're doing both kinds of problems with every problem you have for practice. I will always do the problems symbolically first. All right, so there's a force this way. And if I was to draw the spider from the side, he's experiencing actually three forces. Weight downwards, normal force upwards, and some force towards the center, and I'm sure it's friction. That's what's holding that spider on. Questions about that? It's static friction, because he is not slipping with respect to the record. All right. I've drawn my three forces. I'm going to say this is a net force equals MA problem. I'm going to draw a coordinate system that I could use to solve this problem. Do all of these things sound like the things I do all the time for these problems? I really hope so. You have a procedure. I hope you're following it. I am going to make the positive x direction the direction of the unbalanced force, because that has to be the direction of the centripetal acceleration. Again, no surprises, right? My positive x direction is my direction of the acceleration. I will start with net force equals MAC, and this is in the x direction, and net force in the y direction therefore equals 0. I will identify the forces that are acting in my system. Friction. That has to equal, I might as well put it in, m omega squared r. I'm going to use omega because omega was given in the problem. We still good? I can see right away that for the bug to walk away from the center, the frictional force is going to have to increase. And it's a linear relationship. Do you see that? It's right here. If r gets bigger, that has to be bigger to hold him in place. So we have a limit though. We'll get to that in a minute. Y direction normal equals mg. Right now, you can't solve the problem. You need to identify a way of working the coefficient of friction in, which is clearly a part of this problem. This doesn't demonstrate any limits. Right? We're talking about limits here. The limiting factor of this problem is about, whether the spider can actually continue to stay where he is. So a limiting factor has to be something you kind of can express. Now, somebody in tutoring last night asked if the limiting factor in this problem is if the normal force is 0, a massless spider. But if the normal force was 0, the spider couldn't stay on the record because the friction would be 0. So that seemed a little ridiculous, but they were trying to grasp at the straw, right? We talked about a limiting factor yesterday or the day before that had to do with the normal force going to 0. That's not this problem. I need there to be a normal force, there's a frictional force. But there's something I haven't used yet. I haven't used this. And there's limits in this one, isn't there? I got that less than or equal to limit. That tells me quite a bit. And I've kind of expressed this before. I think it's always best to plug into your inequality so you know what things can get bigger or what things can get smaller. So we're going to plug into this inequality to find a relationship. So m omega squared r must be less than or equal to mu s mg. This problem was about the coefficient. So I'm going to cancel out the m. I'm going to solve this for the coefficient, and the coefficient must be greater than or equal to omega squared r over g. Greater than or equal to. That tells me the smallest one is the one where it is equal to. It can be greater than that, but the smallest one, the minimum coefficient of friction, is when those are equal. Right? It says it right there. When you solve it for the inequality, you know exactly what it's trying to tell you. There's the answer. And when they give you the coefficient, you can immediately put the new coefficient in and figure out where r has to be. Without having to do any more work. Just solve it for r. I guess it's a little more work. How's that? Is that a good enough explanation to answer everything? Yes, Christopher.
You go over the second part of the problem? Actually, did you cover
No, I just did the second part of the problem, and I don't remember what the second part of the problem is.
it? It gives you like the coefficient of friction, which is 0.22, and then you just put it in. Now, I don't know how you do the rotation.
You want me to do a conversion?
No,
I don't know what you want from me. I'm asking, what do you want from me?
like, you know when you like,
You use the word like one more time, the answer is no.
do you know when you plug in the numbers or Alright, never mind.
I'm just waiting for the question mark to come out. Yes, sir?
Do you plug into 33 1/3 into omega squared? Do you have to convert it to radians per second?
It has to be radians per second. Anytime you use omega in a function like this, it has to be in radians per second. And there's a couple reasons, but I think the obvious one is that G is in seconds, right? That's part of it. Also, this has to be a unitless quantity, and rotations isn't a unitless value. It's a value. Radians is a unitless quantity. The meters already is canceling out. Yeah,
Would you have to convert the 12 centimeters into meters?
you would. You would. So maybe the numbers are important here. But yeah, you'd have to do 33 1/3 rotations per minute, and you'd have to convert that to radians per second. I was not planning on doing that part. If you need me to, I will, but I don't think that's what Christopher's trying to get me to do. Yeah,
What were you thinking as a G for this
I'd go with 10.
problem? 10?
Functionally, on any problem, just use 10 for acceleration of gravity.
Okay.
Yes, Christopher.
That's-
Is there a question mark at the end of the sentence you're going to use?
Yeah.
Okay.
May you please convert from rotations per minute to radians per second?
Sure. And Christopher, I'm doing this for the last time. Write it down. How to do it, not what I do. Please. And I'm saying that because the next time I'll probably say something that you'll regret or I'll regret. And I have tenure, which means they can't fire me easily. So, and I recorded that. I can't wait for somebody to hear that on video. I want to cancel the minutes and be left in seconds. So that's going to be a unit multiplier. I use unit multipliers. And because I use unit multipliers, I am seldom wrong when it comes to conversion. Nothing should make you look sillier than getting your conversions wrong. Do you understand my meaning? Because it's something that's just so beneath it. At homework, you've got Google. Just ask it. 33 1/3 RPM per minute to radians per second. It'll just tell you. But on the test, you'll have to do this. So every time that you use a unit multiplier, you are converting by one step. You'll have to know the conversion to make that step work out. So if you don't know, say, hours to seconds, you might have to walk your time through middle steps. But you put what you want to eliminate on one side of the fraction, what you want to be left with on the other side of the fraction, and then you use your conversion fact. There are 60 seconds in every minute. And I'm telling Christopher this, and he's not even listening. He's got his head in his bag. The next conversion I want to do is to get rid of the rotations, because I want to be left in radians. So rotations and radians. And again, I need a conversion fact. For every one rotation, there are 2 pi radians. And that's it. Multiply across on the top, multiply across on the bottom, get yourself a number. And no, I don't care what the answer is. You should care. Well, at least you should care more than I do. All right. That problem was fun. Now, all of you are probably thinking, I don't have the time to give you a quiz. Nothing could be further from the truth. I am sure in these 8 minutes, I could glean something from you. I'm joking, I can't. So you will have a quiz, the first to the same for both of them. Now, when the car is at the top of the hill and it's trying to go over the hill, it's going to experience a normal force that must be less than the weight. Must be. So that the unbalanced force can be downwards. Now, we did this problem with the Ferris wheel, and then we did it with roller coaster stuff. It's the same problem. When I consider the net force on the car, mg minus n has to equal mv squared over r. Intentionally making downwards positive. Now, for the dip in the road, I need the normal force to be greater than the weight. I need the unbalanced force to be upwards. And in this circumstance, I'm making upwards positive because that's the direction of the acceleration. Now, in both cases, I'm supposed to solve for the normal force on the car. The answers are different. Not by much, but in a very critical way. Assuming the ground can continuously provide support to a car, you can go as fast as you want through the dip, as long as your suspension can handle it. Right? If your suspension can't, you'll bottom out at the bottom of the dip. On the other hand, going over the top of the hill, you have a limiting factor. There is a possibility as you go faster that this will eventually approach zero. When it approaches zero, you're no longer in contact with the ground. And under this circumstance, a normal force can't switch direction and pull you downwards. So if you go faster than this, you're definitely leaving the roadway. Your limiting factor is whatever makes that zero. Now, I'm not saying set the normal force to zero. I'm saying that the faster you go, the less the ground has to support you. Eventually, you will run out of support. Up with a minus sign and an arithmetic expression should cause you to pause. There's probably going to be a question about it. I never stay away from a question I know it's going to come up with a negative sign somewhere in it, because it's going to be purposeful. It's not there by accident. A negative sign means that the result of this can be positive or negative or zero, depending on the conditions of the problem, which probably means that you have the possibility of something changing in your problem, depending on what you choose. In this case, it's how you choose how fast you go. So trust me when I say this is the kind of problem I'm going to play with for sure. And AP loves this kind of stuff. They're going to be all over problems that have threshold. All right.